Alright, hello and welcome back. I know that the last lecture took the full time, so this time, this one will be a bit shorter, I think. I will promise that. This lecture is about loops, and this is awesome. This allows us to get the full power of our computers now, finally. There's no program that we can't make after we learn loops. It might be hard, and it might be easier to use some stuff that we learn about later, but every program is representable using what we have learned after you learn loops. And loops are just a way to keep coming back to a same spot, to a place that you were at before. So with that, let us get started. So, to motivate this, remember the guess the number game that we were doing last time? I had to copy and paste code, and that was so silly. That was so silly because, I mean, there's still a chance that the user, maybe they just guessed the same number as many times as I copied the code, then the program would end and they would never be able to win, you know? So copying and pasted code is not a good idea. Copying and pasting is not the solution. So it would be nice if we could just make our programs revisit the same code, okay? Existing code, okay? Rerun, revisit, existing code, until we tell our program to stop going there. All right, so right now our programs are a combination of straight lines and branching. They look like this, in essence. The last piece of the puzzle is this. And you can have branches inside of this, but this is the idea. That is what we cannot do yet, and this is what we want. Okay? This is beautiful. We want this. Okay? Maybe I should draw a box. Okay? So we would like to do this. That is the idea. And so, yeah, we'd like to add these things called loops. So, I mean, let's go right on into it. I'm going to show you a new type of syntax in C++. This is called a while loop. Okay? And you read it like this. While this Boolean expression, while that's true, execute the body, please. Okay? And then once it's done, once it finishes, it'll do the rest of your code. That's how you read it. While the expression is true, please execute the body. So, pretend that, I don't know, our program, there was something before it, like A or something. Like there were dot dot dots here. So here are the dot dot dots. This is what the program will look like when we run it. Say dot dot dot. Then we will check the Boolean expression. This is what the while loop does. If it's true, it will execute the body. And then, after the body's done once, it'll go straight back to the condition, check if it's true. Keep doing that while it's true. Okay? And then once it's false, it'll start doing the rest of your code. Okay, so maybe it's supposed to be like a straight line, so this is the rest of code. So the second it's false, it continues with the rest of the code after the while loop. The while loop is completed at that point. Okay? So that is a lot of words. Let me show you this in action. We're going to do a demo that sums the numbers. Well, let's print them first. We'll print the numbers from 1 to 10. Okay? And so we want to do this. 1, 2, 3, all the way to 10. Okay? That's what we would like to see on our terminal screen. Let's make this happen. Oh, and I think I just messed this up, so let's fix that. There we go. All right. So cd CSCI 40, make dir lec 06. Now I'm going to make a new file called while.cpp. Okay. So we're going to print the numbers from 1 to 10. And the way we know how to do that right now is ugly. Cout 1. Cout 2. Cout 3. Oops. Dot dot dot. We don't want to have to do this. but given what we know, this is all we can currently do. Okay. Oops. There we go. So, what's the secret? We have to use this while loop thing. And we know how it executes, but what's the strategy? How can it... Sure, I can put something in the body and it'll execute every time, but how do I make it different every time? And this is where variables come into play. So let me make an I variable, and we'll start it out at 1. Okay? And then we'll print I, and then to get ready for next time, we'll increment it as well. Yeah? Does that game plan make sense to you? So I'm going to make this variable called I, and I is the common thing to use. We started at 1. Naming this variable I is, oh no, it's customary. It stands for iteration variable. And loops, we say that loops iterate. Like they keep coming back, all right? So while something, I want to print I, print my current value of I, and then I want to increment I to get ready for next time. For the next iteration, we say, of this loop. And so we'll just do I++. All right? So now the question is, what in the world do we put here? Because that expression, this Boolean expression here, as long as that's true, we execute our body. And we want it to stop, we want our loop to stop once we hit and print 10. Okay? So maybe we can say something like this. While I is not 10. Something like that, maybe? So this will keep executing the body while I is not 10. Yeah? And it'll start out 1, so that's okay. And so it'll print 1, make I 2, come back, check. Yeah, it's not. Keep going, keep going. So let's actually execute this code on paper, because that's how we learn. All right, so what's going to happen is in the first iteration of our loop, we will do the following. So we initially set it to 1. So our loop will first check the condition to make sure it can run its body. Is I not equal to 10? Well, yes, 1 is not equal to 10, so it'll execute the body. So check I not equal to 10, that's the first thing that happens. And now, it's because it's true, we'll execute the body, so we'll print 1, and then make I 2. Increment I, so now it becomes 2, and then we'll go back to check, hey, is I still not equal to 10? And it's not, it's only 2, so we'll again execute the body. We'll print 2 now, and then increment I. So print 2, increment I, so now it's 3. And I think you can understand that what's going to happen, at least until it becomes 9, is the following. It will print all the way 1, 2, 3, 4, 5, 6, 7, 8. And then when I is set to 9, we'll check, is I not equal to 10? No, it's not. So we'll execute the body, so we'll print 9, increment I, and then again, go back. Is I unequal to 10? But we just incremented it. It is 10. So then we stop the loop without printing our 10. Okay? So the actual thing should be y is unequal to 11, oops, 11, or alternatively, and the more common thing to do, is saying while I is less than or equal to 10. We want to always do this body. Okay, so now if I run it, oops, and make it large, so now when I run this, I need to get into, oh goodness, I think I might have done something horrible. Yeah, I made this in my CSCI 40 folder instead of my Lecture 6 folder. So I'm going to move this file into there with the move command and cd into Lecture 6 folder so that I don't mess that up ever again. There we go. As we were. G++, standard equals C++ 17. While.cpp dash oh while. And oh man, do we get what we wanted. We print 1 because it's still less than or equal to 10. We'll execute the body, which increments I, makes it 2, ready to be printed out in the next body iteration. Then we print 3, increment, print 4, increment, print 5, increment, all the way, print 9, increment. Now we have I equal to 10. Is it less than or equal to 10? Yes. So execute the body one last time. And so we'll print I, increment I, and so now we stop the loop, because once we check again, is 11 less than or equal to 10? No, it's not. So here, once we get here, I is equal to 11. Okay? And I can prove that too. See out last value of I. It really is 11. Okay? Printing from 1 to 10 with a while loop. And this is saving us a lot of typing, especially if this was a large number like 100. Okay? The next thing that I want to do is sum the numbers from 1 to 10, and we're going to do the same thing. We're going to keep our I around, because that's the number we're currently trying to add to something, but we also need another variable in this case. So I'm going to have my I, and then I'll also have a sum variable that we're going to add into. And so the game plan for this is, well, start I at 0, or start I at 1, then start sum also at what? Well, not also, but what should we start sum at so that we can continuously add I into it and have it be the correct value? I think we should start it at 0, yeah? 1, 0. And then, while I is less than or equal to 10 again, do the following. The first thing that we'll do, oh darn, I can't tab over for this. That's quite unfortunate. I'll just use spaces. While I is less than or equal to 10, the first thing that we'll do is add I, add our current value of I, into sum. Okay? And so in the first iteration, sum will be 0 plus I, which is now 1. Then we want to keep adding after incrementing I. So now we'll add 2 into sum, which will make it 3. Then we'll add 3 into sum, which will make it 6. Then we'll add 4 into sum, which will make it 10, etc. Okay? And then, to make sure that we add the next thing correctly, we'll then increment I as normal. Alright? And so after this is all completed, then sum will hold all the values from 1 to 10 added into it, so 1 plus 2 all the way on to 10. So at the end, sum will have equaled, will have become 1 plus 2 plus ... all the way to 10. All right. And I know there's a formula for this, so we didn't have to use a loop, but this is more fun. All right. So now let's sum the numbers from 1 to 10. And We can reuse the I variable, but I want to keep it there for you. So let's use j instead. So that we have a new variable to work with. We didn't need to make j though. So I'll say int j equals 1, int sum equals 0, while j is less than or equal to 10. This will allow j to range between, so j will be allowed to range between 1 and 10 inclusive. We're going to add j into sum, and then we're going to increment j. Okay? And remember that this line is equivalent to sum equals sum plus j. And then we'll advance j to be the next number. And so now, oh, that's really ugly, sorry. How about that? Hopefully, with my explanation, it'll make sense when we print out sum and the sum is 55, which is the correct answer. Okay, so it kept adding into sum the current value of j, and j was allowed to range between 1 all the way 2, 3, 4, up until 10. It was allowed to be 10. And then it stopped. Then the loop stopped and we printed the sum. So now, j, again, is 1 more than it was. Because this loop stopped, we know that this condition is false. So if this loop stopped, doesn't have to, we know, and that's key, we know that the condition must now be false. So, not j less than or equal to 10 is true, or alternatively, j is greater than 10. And the way that we incremented j, we know that j will have to be 11. Okay? So, I'll say last value of j now. So, the last value of j will have to be 11 again. Okay? So hopefully you understand what's happening here. We started with j equal to 1, sum equal to 0, and we kept checking. Hey, is j less than 10? Yes, it is. Added into sum in that case, so sum becomes 1. And increment j, and then go back to the while loops condition, because that always gets tested before we execute the body. This is the body. J is less than or equal to 10, added into sum. Sum equals sum plus j. So it was 1, now it's 2 more, because we added the 2. So now it's 3. Then we increment j, j becomes 3, still less than 10, added into sum. Sum becomes 6 because we're adding 3 more to it. Okay? And this will go down until j becomes 11, that'll stop the loop, and then sum will become, was it 55? I think so. Yeah. Okay. So, yeah, that's loops. That's the first kind of loop, and every loop that I'm going to tell you, there's also a thing called a for loop. Those are all equivalent. So, you can get by only ever using this while loop. Alright? And this is like a big day for us, because you might not care, but if you do, you might have heard of someone called Alan Turing, and the Turing test, and the Turing machine, which is a model of computation. So every computer ever made can be modeled by this thing called a Turing machine. I'm not going to test you on this. This is just for your knowledge. So our knowledge of C++ at this point allows us to simulate any Turing machine. So every single program that could ever be made or ever will be made, our knowledge of C++ can program it. So isn't that a cool thing? Now, you might think of, well, why don't we stop the class at this moment? Well, there are a lot of other features that, slash ideas, that will make your life a whole lot easier. And so that's why we don't stop the class right now. But I just wanted to let you know that you can make every program ever. It might just take you a long time. You know enough to simulate any Turing machine. So you should be excited. All right, moving on. Let me check the time. Infinite loops. This is actually Apple, because, I mean, they have a lot of money. When they made their campus, they got to make their street as well. So they called it, and their address was 1 on that street, and their street name is Infinite Loop, which is hilarious, after you see this slide at least. So our programs can be wrong in a new way now, and they can be they can exhibit infinite loops. So, like I said, if this loop stopped, we know that the condition must be false, but it's possible for the condition to never become false. Let's watch that happen. Dun dun dun. How do I want to do this? I'll make a new file called infinite loops. Infinite loop.cpp. So, here's a very simple infinite loop. Int I equals 0 while, how do I want to do this? Do I want to make this a real infinite loop for you? Yeah, while I is less than or equal to 10, again, pretending we wanted to print out from 1 to 10, cout I new line. And that's it. So what did I forget to do? I forgot to change I ever. So it'll always be 1, and 1 is less than or equal to 10. So I forgot to change I. So we'll never get here, since I will always be 1, and 1 is less than or equal to 10. Alright, so if I run this program, it will never stop. And be prepared for this. Your programs will exhibit this one way or another. Don't be scared. It's just a rite of passage. So to run this program, it's going to print 1 until the end of time. Whee! There it goes. And you might be scared and wonder how to stop this program. And the answer is Control-C. I must have scrolled off the end. I'm sorry about that. The answer, to stop a runaway program, you say Control-C. Okay? And that's what the caret means, just like nano. So it's running, it's not stopping. Control-C. That stops it. If you're extra scared, you can always just quit your terminal, but that might quit your Vim as well. I don't know. You could also just quit the terminal. That'll stop any program that's run inside of it. Okay? Use Control-C to stop an infinite loop. And get back to the terminal. Okay, so the idea was we had our condition that was always true. Like if you were to say while true, that would never stop. And then there's the body, and this is always true, of course, and it'll come right back. Come right back. It'll never stop. It'll never hit the false case. And that might actually stop the program. Okay, so now you've seen infinite loops. Be aware. Alright, so now something that we will be using later is this algorithm called the greatest common divisor, and it's one of the oldest algorithms to have been invented. So it was invented by Euclid back in the BC era, and here it is. So this is something that you're going to get used to, taking somebody else's idea or algorithm or sequence of steps and writing it down into code, translating English into code. This is called pseudocode. And there's not usually ever a dash, we just say pseudocode. Just one word. Okay, so here is the greatest common divisor algorithm, and what it's going to do is find the largest number that divides two other numbers. So for example, if I had, I don't know, let's say 12 and 18, if you break these down into what they are, it's 2 times 3, 2 2s and a 3. So 6 times 2, this is 2 and a 3 and 6 and a 3. So these are the numbers they have in common. And so the greatest common thing, the greatest number that divides both of them is 6. Okay? That's the idea. Hopefully that makes sense to you. But this is a way of calculating that value, and it's useful to have a lot of the time. Okay. So let us get it. Let's get A and B from the user. I'm going to make a program called gcd.cpp. Okay? So we're going to get 2 numbers from the user, and they're going to be ints. So we're going to get an int A, and then we're going to do the same for the next number. Get our B. Now we have B as well, and now we're going to execute the algorithm. So here it is. While B is not 0, we're going to replace B, and we're also going to replace A. So maybe we want to save those somewhere. So like original A equals A, original B equals B. Now let's do our loop. While B is not 0, right there. All right, that's not hard to do. While B is not equal to 0, we do the following. Replace B with the remainder from dividing A by B. Okay? So A mod B, put that into B. Okay? And I'm not going to test you on how we came up with this. This is like a math concept. It's just fun to use this algorithm. And then we'll replace A with the previous value of B before we took the remainder. So we should have saved it. Okay? Dun, dun, dun. So replace A with the previous value of B before we took any remainders and changed B. So int old B equals B. Then we'll say A equals B, old B. Okay? So save current B so that we can put it in A. Then we replace B with A mod B. And then we replace A with the old value of B. Alright, hopefully that's not too bad. And then when B is 0, A holds the greatest common divisor. It just so happens that these steps make that happen. So when B is 0, this is correct. And what do you know? When this loop stops, if it stops, and it's a whole branch of computer science to be able to prove whether or not your program is going to terminate, which means finish. So if this loop stops, we know that B equals 0 is true, right? Because this while loop's body would have kept iterating as long as B was not equal to 0. So if we ever got here, we know that B must be 0. All right? And once that happens, A holds the GCD, so Therefore, A now holds the GCD of the original A and B. So, let's print it out. The GCD of, and it was original A and original B, is, maybe a colon because suspense, is A. Because A will hold the GCD at the very end. Okay? So with that, here's our whole program. Let's watch it work. Alright, enter A. It was 12 and 18 was my example. And so it'll run this loop. And oh man, is the GCD 6? Isn't that awesome? And we can just type in random numbers. Only two, I don't know, 150. They have 50 in common. 100 and, I don't know, 32 have 4 in common. All right, so that is the GCD algorithm. Let me show you it working for 6, or for 12 and 18. So A is 12, B is 18. We also have this old B variable right here, and let's save that as well. So let me show you that working here. All right, so while B is not 0, it's not 0. Replace B with the remainder from dividing A by B. So A divided by B, remainder, 12 mod 18. Well, that's just 12. It'll actually flip these. So this is now 12. And the old value of B, which we saved right here, is going to get set into A. Right? So now it's 18. And the number's swapped. Now it can actually do the real work. So B is still not 0. Replace B with the remainder from dividing A by B. Okay? 18 mod 12. Well, that is remainder 6. Okay? And then we saved 12 over here, and we're going to replace A with that. Okay? Then replace A, then we go back. Is B 0? Not yet. Replace B with the remainder from dividing A by B. Dun dun dun. Oh, it's 0. Okay, replace, and then we saved the old B over here, and then we're going to replace A with the old value of B, and it holds 6, and oh man, is B 0? And so the GCD is held in A, which happens to be 6. So this works, and it's like a math concept to understand why it works. It's a number theory thing, but that's where I want to leave you. Hopefully you understand how to convert this to code from English, and then now you have an idea of why it works. Okay, let's check the time. Not too bad. So now let's go back to that guess the number game. So we kept on asking the user for a new guess, and then we had to copy and paste that code, but oh man, was that silly. Let us fix that now. We know how. So what I'll do is take what we had from last time. So I'm going to copy lecture 5's, it was guess.cpp, to my current directory, and I'm going to call it guesswithloops.cpp. The better way. So now I have that file. Let's edit it to be all cool and have loops. So this whole part, this thing that I kept copying and pasting, should be inside of a loop. So I'm going to delete all the rest of that. Okay? So now this needs to go inside of a loop. We need to repeatedly ask the user for a guess. While the user is incorrect. And what does it mean for the user to be incorrect? Oops. Guess is not equal to num, if you go back to reading what this all means. So, I want to say something like, while guess not equal to num, do all this stuff. But right now there's one small issue, and it is the fact that guess at the moment is uninitialized. It could be any random value that was in memory, and so it's possible, but unlikely, that it's set to num right now. So we need to make sure that it's never equal to num. So let's start out with a number that can never be the case. All right? Start out guess with a value that is always different from num. Okay? And so because we're getting positive values, if we just give it a negative thing, then we should be okay. Okay? I hope you see why that's necessary. Okay. So now, while the guess is not equal to num, we'll just keep doing this. We'll keep it repeating, enter a guess, get a guess, and then now we'll check. Is the guess greater than the number? We'll tell the user, hey, it was too high. Is the guess less than the number? Okay, it was too low. And then finally, if none of those were true, the user got it after as many times as they needed because we kept repeating while this condition was true. Okay? Isn't that nice? We don't even have to exit anymore because once the loop stops, remember, once we get here, if we ever do, then guess is equal to num. We know it has to be the case because otherwise it would have continued the loop. Isn't that nice? And then the program will just immediately stop. Alright, so let me prove this to you, that it's still working, and that this is the right way to go about it. Alright, / guess with loops. Enter a guess. 50. Let's do the right thing. Or actually, 450. It's always going to be too high. I can do this as much as I want. It'll just keep coming back. I can do -1 as much as I want. It'll just keep coming back to this loop, and it will never stop until I get it. Okay? So let's actually play the game. Ooh. This number is a high one. It was actually 99. Wow, what do you know? What are the odds? So, that's our game. Now it totally works with that while loop. Okay? We ask the user, while they still haven't entered the number correctly, while they haven't gotten it, it'll keep coming back. So, while guess is not equal to num, while that's true, ask and check. And it'll come back here, and eventually it'll be false, and then the program can stop, return 0. Alright, hopefully that makes sense to you. Please come yell at me in office hours if it does not, but that is guess the number. How we doing? Alright, now let's go on to for loops. This is a different kind of syntax. It looks like this. It is essentially shorthand for a while loop, because I just told you that while loops can do everything under the sun. You don't need to actually learn for loops, but I promise that they will make your life easier. Okay? So a for loop has not just a condition inside of its parentheses. It has what I'm going to call an initialization, then a condition, and then this thing that is commonly known as an increment. Okay? So this is what this will look like when we execute it. So if there was stuff before, and then there's stuff after, we can do the before. So we came up to the before. Let's just say this. Maybe I'll put it over here. Before. Then, the first thing that happens is the initialization of a for loop. I'll call it init. And that only ever gets run once. Init only happens once, even though this is a loop. Init, then, like a for loop, it checks the condition, or like a while loop. So it'll check the condition. If it's true, it'll execute the body. And then after all of that, and I guess I do need some more space, and then it'll execute this increment statement as well, which is now been picked out of the body. It's separate. Then the increment always, and then it'll come back to the loop and check the condition. And if it's ever false, then we're finally done. We could do after. Okay, so that's a for loop. The init happens once, and the rest is a loop. Check the condition, execute the body, run the increment statement as long as the condition was true. And then finally, once it becomes false, then we can stop the loop. Okay, so let me show you printing from 1 to 10 with a for loop. All right. I'll make a file called for.cpp. So let me show you while one more time. So int I equals 0, I equals 1, while I is less than or equal to 10, cout I plus plus. So what I'm about to write is equivalent to this. So darn. Okay. So now for int I equals 1. That's my initialization. Start out I, please, at 1. While I is less than or equal to 10, execute the body. And after you're done the body, I want you to increment I, just like that. So everything that involves I and manipulating it and testing is done up here, inside this parenthesized thing. So it kind of like separates the logic of the body from the logic that involves I. So all we have to do in the body now is print I. Okay? We're going to have to increment because it's going to be done for us. And we never had to initialize I outside of the loop. It'll be done for us there. Okay, so now let me just prove to you that this does the same thing, and then I'll walk you through it. So it does in fact do the same thing, but why? Why in the world? So let's do this. So what's happening here is, well, maybe you can look at this slide while I keep this one up. So this is what's happening. So the first thing that we do is our initialization. And let's see here. Initialization happens first. This is init. This is our condition. This is our increment. And this one thing, this line, is the body. Okay? That one thing is the body. Sorry, that's not extra visible, but that's as good as I can do at the moment. So the first thing that happens is it makes a new variable called I and sets it to 1. And then it checks the condition. The condition is true. 1 is less than or equal to 10. So it'll execute the body once, which involves printing I. Okay? Then it goes and does the increment statement. And you can see how this, like, you'll eventually grow to prefer this, I think, for simple loops like this that involve incrementing and iterating. So then it increments I to be 2. It's still less than 10. Go back to the condition, print it out, run the increment statement. Again, so now it's 3. Go back to the condition. It's true, so print it, and on and on and on until the edge case, until we get to, let's say, 9. So I is now 9. 9 is less than or equal to 10. We'll print it, because we execute the body. I++ makes it 10. It's still less than or equal to 10. Print it out. And increment I one last time. And now when we go back to check this final condition, it's false because 11 is greater than 10. It's not less than or equal to it. Okay, so hopefully that makes sense, and that's why this for loop does the same thing. And in essence, what it's doing is it makes it so that you can put the I, the thing that the loop only cares about, only I matters inside the loop. So you can put it inside now with a for loop, and the body stays the body. This increment thing that involves I gets shoved up into the parenthesization, like this parenthesized statement, and the condition kind of stays up there as well. Okay, so it's kind of like put all the I manipulation stuff up in the start, and then all the real logic of your program goes inside the body of the for loop. Okay, but it's all equivalent. It's just moving stuff around. And so there's always a way to convert a for loop to a while loop and a while loop to a for loop because they are equivalent. Turing complete. Oops. There we go. Alright, let me keep checking time here. Yeah, we're doing fine still. So maybe this will be where we stop if we get there. So the scope of variables. Now this is something I want to talk about because we're making variables that loops are using. And so we've also added if statements to our repertoire. When we make braces, we can create variables inside of them, okay? Just like a main function. Technically, a main function is some braces. All right. So the variables that we make inside of braces live only inside of the inner brace. Okay. So let's say I have a bunch of braces somehow. Maybe they're if statements, maybe they're while loops, and I say int I inside the third one. That's an ugly last one though. And I say int I in here, and then I have a closing brace, and then some stuff, then a closing brace, then some stuff, and then a final closing brace. Well, I only lives in between its innermost braces. Okay? So if you talk about I out here and there wasn't a separate I, the compiler would complain. It wouldn't even compile your program. So I only exists in between its braces. Okay? And so you can make a variable inside of what we call, this is like a scoping thing. So when I say scope, I mean like which variables are alive at the moment. Like what can you see inside of these braces? What is visible? I guess that's more of related to the etymology of the word scope. What you can see. So just remember about these variable lifetimes. And if you ever make an int I here, and then make another int I in here, inside of these braces, you're getting this one. Okay? You just shadowed the outer one. So try not to do that. Okay? I should give you a few examples of this so that you understand it. And the first one is actually here already. Inside of a for loop, notice that I was defined inside of the for loop. It does not exist in main. So the following, see out I, might expect it to be 11 like it was in the while loop, but I doesn't exist out here. I was not declared in this scope. It existed for the for loop, and then the second the for loop goes away, it completes, there is no I anymore. There's no space made for that. So the above is a compiler error, because I is no longer in scope, we say. Okay? And then let me give you a couple other examples of scoping. Let me talk about shadowing. So if I have an if statement, I don't know, int x equals 42, if x is, I don't know, less than 43, int x equals 7, cout x. Actually, I'll say inner x. And this one will be outer. What do you think is going to happen here? Well, just as you might expect, this x, the inner x takes precedence. The closest x always is what you get. So you have just shadowed this definition, this declaration, shadows, we say. Oh darn. That autocomplete, not very nice to me this time. This declaration shadows the outer x. So when we're in here, we get the 7. When we're out here, we get the 42. All right? So hopefully that makes sense to you. The best thing that you can do to save yourself so much debugging time is to never use the same variable inside of the same function. So here's main, I've got my x. I am never making another variable called x. Just make that your life's motto from now on, if you can. Alright, so that's the scope of variables. And then, let's see, sorry, I'm impulsively checking the time. I think I'll do this, and then we'll be done. Alright, so I'm going to lowercase a string for you. Let's pretend that our string was something like this. Blah, all caps. And then we want to translate this somehow with magic, of course, but really just C++. And we're going to turn that into lowercase blah. Okay, and so this involves, we know how to do this for one character at a time. We can go to the 0th index, make it 2 lower. Yeah. We know how to do this for one character at a time, but now that we can iterate, now that we can use loops, we can visit every single index and call the 2 lower function. Okay? That's all we have to do. So, game plan. That's really tiny, sorry. Game plan. Still very tiny. How about that? Visit every index of the string and call the 2 lower function. Okay? To reset the character there. Alright? This is how we lowercase a string. I'll call it lowercase.cpp. And so we're going to use strings, so we're going to need string. And we're going to use lowercase, so we're going to use that 2 lower function which exists in the CC type library. Alright? For 2 lower. For the string type. Alright, so I'm going to make my string, or maybe we can have the user enter one. And when we get strings from CN, remember you only get one word at a time. So CN, or string S, CN S, and now we'll capitalize that. We will iterate through, that means visit all indices of the string S and call 2 lower to reset the character there. So, how do we get through this entire string? Well, we need to know how many times our loop needs to execute, okay? So, here's my string. Index 0, 1, 2, and 3. How can I make sure that I only ever go in between 0, 1, 2, and 3? I think you know now. You can use an iteration variable and make I start at 0 and always be less than the size, strictly less than, because the size is 4. Alright, so int I equals 0 while I is less than s.size. So we'll iterate we want I to range between over all valid indices in the string s. Okay? So now it'll go between 0 and size -1, because we're saying less than, strictly less than. And then we'll go and say s.at I, so at the current index, lowercase the character. Okay? So s.at I equals s.at I, whatever it was, but 2 lower. Okay? And then finally we can output s. Enter a word, blah. Oh shoot, let's see what I've done. Oh, guess what I have? An infinite loop. I++. Blah and little blah. Okay, and this will work for anything. So let me show you why it works. So this is what we're doing. We have our I, and we started at 0, and we had our string s, which is blah, and s.size, that is equal to 4. There's 4 characters in this string. So in the first iteration of the loop, we visit the 0th index, because I is equal to 0. So at s of I, we lowercase. We call 2 lower and set the value again. Okay? And then we increment I. Oh, sorry, now it's 1. It's still less than 4. So we go to that index, index 1, lowercase it, now it's an L, a little l. Increment I, still less than 4, little a. Increment I, still less than 4, little h. Increment I, equal to 4, that's not less than 4, so we stop. And we don't try to access indices that aren't ours, or that aren't there, okay? So that is that. Just very quickly, I want to show you that you can also do it with a for loop, or you could do the following for loop. For int I equals 0, I is less than, let me maybe capitalize it with the for loop. So we'll say, for int I equals 0, I is less than s.size, I++, s.at I equals to upper s.at I, and then we don't have to increment I, it's already being done for us. Then we'll output s one more time. How about that? So now, when we run this program, it shouldn't be called lowercase anymore, but that's what we get. If I say BLAH like that, it'll go through all the indices, first lowercase them in the while loop, and in the for loop, it'll make them all uppercase. Okay? So hopefully that's an exciting thing to want to do, and go and have fun converting things. And with that, that's where I want to stop this week, so I will see you later.